So this is a good place for us to talk about why the relativistic wave equation fails as a quantum mechanics equation. Okay. So this is my next topic, the failure of the relativistic wave equation as a quantum mechanical equation. Okay, but before I go there, maybe we should take some questions. Okay, so let's revisit the way let's revisit the way we derived way we arrived at the Schrodinger equation, but in a relativistic setting. So the relativistic expression for energy for a free particle is given by E is equals to square root of P squared C squared plus M squared C4. So if I use the de Broglie-Einstein formulae, then the left-hand side is h bar omega. On the right-hand side, I have inside the square root h squared k squared c squared plus m squared c4. Now, if I demand that we get this energy expression from a wave equation, we run into a problem. And the problem is that on the left-hand side, we are going to have a first derivative, time derivative, whereas on the right-hand side, we are going to have a second space derivative, but it'll be inside a square root, right? So it's and it's very hard to interpret square roots of differential operator. Okay. Square roots of differential operators are problematic. And not only that, if I, in some limit, say small momentum limit or something like this, expand this square root, then in principle, I will have an infinite number of terms, of derivative terms. And therefore, I will have, in principle, I might need an infinite number of initial conditions. So the whole thing kind of falls apart. So the way out of this is to take the square of this equation. If I take the square of this equation, so E squared is equal to P squared C squared plus M squared C4. And then using the Einstein-de Broglie relationship, we get H squared omega squared equal to H squared K squared C squared plus M squared C4. Now, using the same argument as the Schrodinger argument, we arrive at the wave equation where we have H squared here, del squared psi del T squared minus H squared C squared Laplacian of psi. So I've brought this guy over to this side. And then we have minus M squared C4 psi. So this is going to be my new wave equation. Now there's a wave operator which is invariant is relativistically invariant, and it's called the D'Alembert. So that, well, the D'Alembert is relativistically invariant only when the speed of the wave is the speed of light. So we define the D'Alembert to be this thing. Then we can write the wave equation in a more succinct form. Box of psi is minus some constant m squared c squared by h squared, psi equals to 0. Yeah. I'm more used to units in which c is equals to h bar is equals to 1. But anyway. So this is a relativistic wave equation. And this equation is a very famous equation. It's called the Klein-Gordon equation. Okay. Now, if I want to derive from the Klein-Gordon equation an equation of continuity, we can do so. All we need to do is to multiply the Klein-Gordon equation by the conjugate of the wave function. And take its complex conjugate. And then subtract it, one from the other. Then, of course, these guys cancel out. And we end up with an equation which, after a little bit of manipulation, is exactly the wave equation, sorry, the equation of continuity. But because the Klein-Gordon equation was a second order equation in time, see? Second order in time, the rho that we end up with is something over c squared, 1 over c squared. I don't really care about the c squared, but it's going to be psi star, the time derivative of psi minus the time derivative of psi star times psi. And the current density is psi star gradient of psi minus psi del psi star. But you see, the rho now has two numbers in which are, complex conjugate of each other, but there's a minus sign between them. So rho is not necessarily positive definite. Okay. And because of that, we cannot interpret the Klein-Gordon equation as a quantum mechanical equation, okay? Because we don't have the Born interpretation anymore. It does have interpretation as a quantum field theory equation, but that's another story. Okay? So Schrödinger actually had discovered Klein-Gordon equation, but he had rejected it because he was not getting physical answers. Okay, any questions so far?
Sir,
Okay,
I have a question.
Yeah.
In the equation E equal to root over p square c square plus earlier in the
Yeah.
so shouldn't there be a plus v, like some potential term?
Yeah, you can introduce that. Yeah, you can introduce that. But I'm just like looking at the most easy, the free
If we
particle.
do that, if we do that, then like squaring on both sides, like the calculation would not be like this, like
It would be more complicated. You're right.
more
Yeah.
complicated. Yeah.
Yeah. Yeah. But it fails even at the level of a free particle.
And I just wanted to say that I saw a paper a few days ago where they tried to formulate probability with complex numbers. Like,
Oh, people
uh,
are trying to do that all the time, yeah. But that's like not canonical. I mean, there are different formulations of quantum mechanics, right? So there's quantum mechanics which, for example, there's a PT symmetric quantum mechanics, which have different postulates than the standard quantum mechanics, right? Yeah.
so I have a question about that. Like, what does different formulations of quantum mechanics mean? Like, we assume different axioms and all that, but I mean, fundamentally, when I, they're all equivalent, or they have to be equivalent, right? Like,
Well, yeah, there are two ways of having different formulations of quantum mechanics. One is that you demand it to fit the real world. And then there are several different ways of looking at quantum mechanics. And they all give the same predictions. Some of them have different advantages in terms of conceptual framework. And there are other versions of quantum mechanics where you describe possibilities that nature never took, but which are consistent possibilities nonetheless. So versions of quantum mechanics which may not fit our world, but which are consistent nonetheless. As theoretical physicists, we don't shy away from formulating consistent theories, regardless of whether it's applicable to our world or not. And when we do that, we are more like mathematicians. We are exploring consistent structures. When Cardano and all those people discovered complex numbers, there wasn't really a very good, quote unquote, application of complex numbers, right? That didn't stop them from doing that. And so you never know. And, as intellectuals, some of us are really interested more in logical, possibilities. So, when a mathematician works on some higher dimensional space, we don't ask them, why are you doing that? It's just interesting. So there are physicists who work on those kind of stuff too. Okay, so that's a field called quantum foundation. And the thing about quantum foundation is that it's only by exploring and understanding what is not, we understand what is. Right? I mean, by understanding what was possible, but nature didn't choose in our universe, sheds light on what is possible, why our world is the way it is, right? Maybe there are other universes in some so-called multiverse where those possibilities are realized. So, for example, string theory predicts a multiverse, many, many different universes. And while the quantum mechanics is more or less the same, but the constants of nature, the grand unified theories for those different universes are different. Okay. Any more questions?
Is this lecture, sir? Yeah, is this lecture on the Powell and Chrisman, or that book, or?
Oh, this one is, I think so. Yeah, Powell and Chrisman. Yeah. Well, I drew upon many different things. Like, for example, the part about the second about the relativistic equation. I just it's not from any book.